Hello, welcome back. I'm going to wait till those people to come in and sit down. So before the break, we heard Mark Hamill talking about Thread Exchange. It's really popular. There was a line waiting up to talking to him. So sign up on Thread Exchange. You can also just catch him after our talk. Next up, I want to introduce Jonathan Gross. He manages the platform integrity team here at Facebook up in Seattle. He's going to talk to us about the lessons learned from his team about fighting platform spam. Thank you. Welcome, Jonathan Gross.
All right, thanks, Christy. Hi, everyone. I'm Jonathan, and I've been fighting spam at Facebook for more than 4 years. And today, I'd like to tell you about some of the challenges that the Facebook platform has presented in terms of spam, and some of the strategies that we've used to overcome them. And in fact, I think you'll find that a lot of the things that I talk about are similar to things from previous talks. So that's going to be pretty interesting as well. So what is the Facebook platform? The Facebook platform encompasses all interfaces for third-party developers. At its core, it's how data gets in and out of the Facebook graph. And the Facebook platform has several different components that introduce various attack vectors. And there's 3 that I will talk about today in this talk. First, there's the API and the application model, where applications can themselves be malicious. And second, I'll talk about social plugins for websites and some of the challenges that happen there. And third, I'll talk about an type of attacks on the authentication mechanism that the Facebook platform uses, where attackers try to steal sessions for legitimate applications. And the first 2 are problems that today we consider in some ways essentially solved. But the third is something that's still very much ongoing. So let's start by talking about malicious apps. Here's an example of what spam looks like on Facebook from a malicious app. And it has 2 important components. There's the creative hook, the promise to be able to see who viewed your profile on Facebook, and there's a link back to the app. And you can notice that this story was posted by an app called See Who Viewed Your Profile. People want to click on that because they want to see that one weird trick to see who looked at their Facebook profile. That's pretty compelling. Now, of course, that's a false promise. But you'll notice here that this post is created by my good friend Maria, who is definitely a real account and not my test account. And you'll notice that I'm tagged in this post, which means that it can reach my friends as well as Maria's friends on Facebook. So that makes it a great distribution mechanism for spam. What happens if you click on this post is you'll end up in the victim flow. So first, you'll be prompted to install that Facebook app and authorize it to post to Facebook on your behalf. And then you'll be actually redirected to the monetization scheme, which is where the attackers make their money. In this case, you end up on a page that says you have to fill out a survey in order to see who looked at your profile. And at the end of that, I promise you won't actually see that. And once you hit OK in that dialog, at that point, the app has full control to do anything it wants on your behalf to your Facebook profile. And of course, this creates a viral loop where the attacker can acquire new victims and generate viral web traffic to make money. What can we do about this? There's one really easy solution. We can review all the apps on Facebook before they go live. And in fact, that's what we do today. We started doing that about a year ago. We introduced an app review process. But the Facebook platform was live for years before that. The Facebook platform was originally designed as an open platform where anyone could create an app. And we weren't ready to have a review process right away. So not long after we launched the platform originally, attackers figured out how to abuse the system to launch malicious apps at scale, which necessitated us building the app enforcement system. And it has 3 major components. First, we measure an app's activity and build up reputation signals on the app. Then, we train classifiers using these signals to decide if an app is malicious. And then finally, we respond by taking down the bad content. I'll go into each of these in a little bit of depth. So when it comes to measurement, we built an event logging framework and integrated it deeply into all parts of the Facebook product. So anytime that any important interaction happens with respect to an application, we log an event about it. So for example, every time the app publishes content through the API, we log an event. Anytime people interact with content posted by the app, when they click on it, when they like it, when they report it as spam, we log an event. And that last part I'd actually like to call out in particular. In Facebook newsfeed, when you see content you don't like, you can provide negative feedback about it, and that gives us an important signal to track how we're doing and also has some correlation with badness. So, okay, great. We have all of these user interactions instrumented. What do we do with it? We feed it into a real-time stream processing system, and where we get time window counters aggregated per app. And that allows us to ask the question, how many times has this app posted in the last hour, or the last day, or the last week, and similarly for all the other signals that we have. Then we train classifiers to decide whether an app is malicious using these features or signals. And we started off by building rules-based classifiers. For example, if an app has posted 100 times per user in the last hour, it's probably spamming. And the nice thing about that is that it's easy to understand. And we got a chance to use all of the great systems and frameworks that the site integrity team has built that they've talked about earlier today in order for us to express and evaluate these rules. And then we actually took the next step of using machine learning. So we actually trained machine learned models to decide whether an app is malicious by looking at its similarity to other apps that we knew were bad. So, we seeded the training data using apps that we knew were good as the ham set and apps that we knew were bad that we had previously enforced on as a spam set. And that allowed us to infer smarter rules about the associations between our features and bad apps. The downside, of course, is that it's harder to explain why the system took action on an app, and it risks false positives. But it was a very powerful approach. Then there's one other important component to this, which is frequent reclassification. We frequently observe new information about an app as it makes API calls, as users interact with its content, so we continuously reevaluate the models to decide whether the app is bad. And that means that we not only make the decision of whether an app is bad at any particular point in time, but we actually decide whether an app is eventually malicious. Once we've made that decision, we spring into action. And the important thing that we implemented here was the concept of a soft disable. What that means is that people can no longer see the app or its content on Facebook. And the other important part of that is that it's reversible. If we ever make a mistake, if we have a false positive, we can flip the bit back, the app and its content comes back onto the site, and we can reverse much of the damage of that false positive. And we have made mistakes. So we've created an end-to-end enforcement experience for affected developers. So whenever we disable an app, we notify developers that it occurred, and we give them a chance to submit an appeal so we can reevaluate their case and restore the app if it was disabled in error. So that's the app enforcement system. We built it. Game over, right? Problem solved. We can all go home now. As most of you surely suspect, that is not exactly the case. So we ended up playing the adversarial game with the highly motivated attackers who were making money off of us. Attackers launched hundreds or even thousands of malicious apps every day, spamming users' profiles on Facebook. We would detect and disable them, and then the attack would renew again. And furthermore, we found that the attackers experimented to evade detection. For example, they would distribute traffic randomly among 100 apps that they controlled, making it hard to aggregate signal on any particular app. They would try varying their posting patterns, try calling APIs in different ways. For example, one day they might post spam in a status update, the next day they might post spam in a photo or to a group post, and there's a lot of different ways that they could actually get the spam onto Facebook. So we took a look at what the attackers were doing, and we had one important insight, which is that every app has to be created by a Facebook developer account. And we noticed that the attackers would typically create fake accounts, but also sometimes use compromised accounts to create apps. And that led us to build the developer enforcement system. So we actually took a very similar approach that we did for apps, and we applied it kind of one level up at the developer level. And in fact, we were even able to reuse the same reputation signals as the app enforcement system, just aggregated at a per developer basis. So we train classifiers in a very similar way, rules-based, machine learning, etc., that would all decide whether or not a developer was malicious and should be hit with the ban hammer. And the ban hammer would have two effects. Number one, it would disable the applications that a developer currently has and prevent them from creating new ones. And that's much more powerful than simply enforcing on a single app, taking down tens or even hundreds of apps at once. So why was this effective? Well, we realized the key insight that attackers will give up when it's unprofitable for them to attack. So we really thought about the economics of an attack. And we realized that the developer accounts are a scarce resource for the attackers. So we made them more expensive. We actually added a little bit of friction in the product to make it harder to register malicious developer accounts, which was to require phone verification. So we required each developer account to be registered by a unique phone number that we hadn't seen before in order to get onto Facebook as a developer. And what this does is create a bottleneck in the attacker's infrastructure where now, in order to launch malicious developer accounts at scale, they also need a source of phone numbers to attach to those accounts. And, well, of course, as the cycle continues, we actually did find attackers buying cheap SIM cards and registering phone numbers at scale, but that's still like a net win for us. We're okay with them doing that because that just comes straight out of their profit margins by launching the attack. And then the other lever that we had was to, of course, reduce the benefit they get from each malicious account. So we worked to improve our detection latency to more quickly take down the developer accounts to reduce the amount of web traffic and distribution they could get before they get caught. And we just did that by iteratively training better and better classifiers until we were happy with it. So we also tried a few things that didn't work, which actually fall into a common theme you've heard from a bunch of other different talks, which are we tried some things that ended up giving attackers an oracle, didn't increase costs for them, and they were easy for the attackers to experiment and get around. So really, the important thing here is that as you try to block an attacker from making a specific API call, it doesn't incur much cost to them. They can just go and try again until they figure out how to get around your classifier. And it's really that tight feedback loop that you want to avoid. Now, I'm going to move on and talk about another type of attack called clickjacking. This is a type of attack where victims get tricked into sharing on Facebook by clicking on a social plugin embedded in a malicious website. So many of you have probably seen the like button on Facebook. It's kind of in a lot of places on the internet these days. And just a little bit of background, the like button is a very simple product. It's actually just an iframe that websites can drop in to allow their visitors to share content on Facebook with a single click. And when you click the like button, your friends see a story on Facebook that you like to link, like you see in the top right here. And it's really easy for developers to integrate into their website. You just drop in the JavaScript SDK and point it at a target URL to like. So let's take a look at an example. What's the first thing that you want to do when you land on this page? Well, you want to play that crazy video of who knows what's going to happen. It's pretty compelling. So what you want to do is you want to click on that video play button. When you do, you're actually clicking on a hidden like button. So what is this attack that we're calling clickjacking? Well, it's a type of what we call a UI redress attack, where a malicious website positions a Facebook like button inside an iframe behind another element to obfuscate the fact that users are clicking on that like button. And the plugin is vulnerable because it can be embedded in an iframe on a website. If you ever build any product that can be embedded in an iframe, you might be subject to this type of attack. Let's take a look at an example code that we actually found out in the wild abusing this. So you can see kind of from the top that the attacker has used some CSS styling to obfuscate the like button, which is inside that iframe in the inner element. They use z-index and opacity and things like that to make it hard to see. And I don't know about you, but to me, a div named clickjack button wrapper 5 seems just a little suspicious. Now, this particular site even has an extra bonus feature, which is they actually make the like button follow the user's mouse around the page by using a JavaScript mouse move event handler to reposition the div. And the net effect of that is that anywhere, if the victim clicks really anywhere on this web page, the like button will actually intercept that click, and they'll like something on Facebook. So that's kind of unfortunate. How can we deal with this? Well, the key, it turns out, is to prevent the element of surprise in the product. Remember how I said that you can like things on Facebook and share with just one click? That was sort of a lie. So anytime click seems suspicious, we built the logic in our product to have the ability to, instead of letting the like action go through, we show a confirmation dialog. And this way, people get prompted with this dialog and they get asked, hey, did you really mean to click like on this? Like, are you sure? And then if they click OK, then yeah, it'll go through. And the key here is that this stops clickjacking by just removing the element of deception. So we're faced with another classification decision. On one hand, we want a smooth one-click interaction when the like button is embedded in any legitimate website. And on the other hand, we want to show the confirmation dialog on any suspicious or malicious one. So what did we do? We built up classifiers based on URL reputation. And in the like button click, in the interaction, there's actually two different URL entities that we can classify on. One is actually the target URL that's being liked and being published by the share. And then the other one is actually the URL that we call the refer URL, which is actually the site that we're seeing loading the iframe. And so we can actually classify on both of those entities in a similar way. So the gist of the classification is that we start off by not trusting new URLs that we haven't seen before. And then we actually build in a feedback loop. After we actually measure the conversion rates on the confirmation dialog as we show it in real time using time window counters. And then once we see sufficient signal of people actually clicking OK in that dialog, we start having reason to believe that that site should be trusted. And then we'll stop requiring confirmation. And in addition to that, we also look for statistical anomalies in the like button clicks that we're seeing. So for example, if a like button deployment has a really high click-through rate, it's probably actually clickjacking. Because normally people don't click on a like button every time they load a web page. There's some drop-off rate. But in clickjacking case, it's actually really high. So finally, there's one other type of attack vector that I'd like to talk about today, which we're calling session theft. This is a case where an attacker hijacks the platform session for legitimate apps in order to post spam. And I'll start this off with a little bit of background on how authentication and authorization works on Facebook. So we use a protocol called OAuth for this. It's a pretty standard protocol in the web. And in this protocol, platform user sessions are represented by what we call access tokens, which are opaque strings that are transmitted to clients to represent the fact that a user is using an app and has granted it permissions. One important thing to think about here is the fact that access tokens are what we call bearer tokens, which means that anyone in possession of an access token string can use it to make API calls on behalf of the user using that app without any other secret keys or any other authentication. So if an attacker can steal a valid access token for you using an app on Facebook, they'll be able to post spam to your profile. And the way that access tokens are actually returned in the OAuth protocol is through browser redirects. So what that means is that the access token ends up in the URL bar of your web browser, and it gets intercepted by the client website receiving it normally. But let's take a quick look at what an example of spam might look like from session theft. So here's a post with a link to some crazy Miley Cyrus video. Oh my God, you got to click on this. And much like the example of that we saw before with spam coming from a malicious app, it's posted by my great friend Maria, and it's tagging me so all my friends can see it as well. But the main difference here is that it's actually coming from not a app called not any particular malicious app, but actually the normal BlackBerry smartphones app on Facebook that many people use to access Facebook normally. What happens if you click on this? Well, you'll land on this page which prompts you to say, hey, you can see this crazy video. All you have to do is give us this verification code on our website, and what could possibly go wrong. So all you have to do is follow these instructions in the website. You say, click here to get your verification code. It'll prop up a window in your browser, and all you have to do is copy and paste whatever is in the address bar into a form on the attacker's site and submit it to them. And conveniently, of course, the string will contain a valid access token for a legitimate Facebook app like the BlackBerry app. So as soon as you copy and paste and hit it, the attacker will get your access token, and they'll be able to use it to post spam. And this creates a viral loop very similar to the other types of attacks we've seen. And it's really a tricky one to analyze and to stop. So let's talk a little bit about what an attacker needs to do in order to actually abuse this. So first of all, they typically have to actually post a link to some URL which contains the landing page with the instructions to acquire new victims. So really, a lot of our strategy in this has to do with identifying these URLs which are associated with patterns of session abuse. And then it actually turns out that attackers kind of have two choices for how they actually use the stolen tokens, client-side versus server-side. They can actually just use the token right away inside the browser to make a bunch of API calls, and then the second the user navigates away from the page, they don't have the token anymore. Or they can actually send the token over to the attacker's server and make some API calls from there. And each of those has kind of like their pluses and minuses. And I'll get into that in a little second here. So what do we do? Our goal is to, like people were saying before, it's actually pretty hard to detect whether or not an individual session has been stolen by an attacker. So we look for patterns. We try to look for patterns of abuse. We try to look for entities to aggregate signal on. So we look at the various metadata that has to do with the way that a access token is issued for a session, and we actually try to aggregate signal on each of those entities. So for example, every access token has an app ID it was issued for, it has an IP address that it was sent to, and then an IP address that's used from, and it has a redirect URI where the token was actually sent to in the browser. And using patterns in this metadata, we tried to identify URLs that are associated with the abuse, and we try to figure out when an API call is coming from a user with a stolen session. So, for example, we actually can do pretty well against the server-side attacks just by looking at per IP aggregation of these signals. Actually, as I think Isaac was talking about before, IP addresses can be a bottleneck in attackers' infrastructure on their servers. But perhaps more interestingly, in some sense, we can try to figure out which URLs are actually associated with spreading this attack by looking at abnormal patterns in the session metadata. So I'll give you a quick example. We can actually write rules that say things like, hey, this URL was mostly posted by platform sessions issued for the BlackBerry app ID on desktop machines. And that's abnormal because the BlackBerry app is not usually used from user agents which are corresponding to desktop machines. But in the case of the attack, it is. So what's our recourse if we detect patterns of abuse? Well, first of all, we can block the API call, but of course it's not enough, so we want to actually be able to invalidate the session. And we have built a system that enables us to do that. And then the other thing is, once we detect that a URL is bad, we'll just ban it from Facebook outright. So there's one other thing that we can try to do here, which is to actually find out and educate victims of social engineering and try to get them to have safer behavior on the internet. But honestly, I think it's a little bit of an uphill battle. I think that, it's hard to educate people about the risks of following instructions on a website, and it's hard to differentiate legitimate flows from those ones that actually do things like steal your tokens. So I can't say we've had a ton of success with education, but I think it's worth trying. So that pretty much covers it for the types of platform abuse that we've seen. And there's a few things that I think are interesting to reflect on as part of our strategy here. So remember, the most important thing that I think we found was that attackers will give up when it's unprofitable. And this is especially important when you're trying to run an open platform. With an open platform, it's impossible to completely prevent the possibility of spam getting posted, right? But if you really think about what motivates attackers, and you really understand how they're making their money and what are their costs, what are the bottlenecks in their operations to launch a spam attack, with those techniques, that can help you find a good approach in order to get the attackers to want to give up. And like we've seen actually in multiple talks today, we found that building up reputation signals on various entities is really powerful. And in the case of many platform attacks, we actually had a really natural entity to aggregate on. In the case of malicious apps, you could aggregate on the app and the developer account. And we also had a lot of cases where we can aggregate on a URL per URL basis. So that made our lives easier in some sense, having nice entities to look at. And then one other thing I want to point out is that product changes are often better than spam classifiers. If you think about what we did to defend ourselves against clickjacking on the like button, if we spent all of our time trying to train classifiers to block suspicious like button clicks, we wouldn't have really gotten very far. But by thinking about how to mitigate abuse in the product behavior and thinking about product design from an abuse perspective, we were able to come up with a much better solution. So that pretty much wraps it up, and I'd like to open the floor for any questions.
Very nice talk. I noticed that you're saying that you banned some URL. I'm wondering, does that allow the attacker to launch some kind of DDoS attack? For example, I want to block my competitor's URL. I'll just do that so that you think it was like attacker URL. You will just block that. How do we deal with that?
Yeah. So the question is about how we think about the possibility of an attacker gaming our enforcement systems to take down legitimate entities. And that absolutely is a problem. And when we actually train and design the classifiers, we very much have to keep that in mind. And so we have to also, in addition to detecting signals that signify badness of a URL, we also work very hard on trying to identify things that are good about a URL and make sure that good URLs are excluded from enforcement. And that's a really important thing to make sure that because if we don't do that well, you're right, attackers will be able to game our system and we won't be able to keep it up.
I'm wondering if you guys have a system for dealing with false positives or an appeals workflow or something like that. A lot of times the trickiest part on things is actually the policy, where it may seem like to everyone in this room that someone is spamming, but maybe it doesn't seem like it to users or to the app creator.
Yeah, that's a great question. So actually, we very much do have an appeal process at both the app and the developer level for the enforcement we do in the platform ecosystem. And we absolutely do think about all of our enforcements in context of our Facebook platform policies. So you're right, it is a little bit hard to define what is and isn't spam. It can be highly subjective. It's kind of the thing that you say you know it when you see it, but it's sometimes a little bit hard to come up with a clear definition. But we have a lot of platform policies that prohibit various behaviors, like automatically posting on the user's behalf without their consent. And in the case of a lot of malicious apps, they would violate that particular policy, so we fall back on that.
On the clickjacking, how do you address attackers basically seeing the dialogue and then having their own users kind of go through that to kind of prime the pump to basically get through the conversion rate?
So that's actually another really good question, because we did in fact see that in reality. And the way that we actually, one way that we were able to mitigate that is by actually looking at unusually high conversion rates on the confirmation dialogue. Because normally there's actually a bit of a drop-off, which means that if you have basically 50 clicks coming in on the confirmation dialogue and every one of them confirms it, that's actually itself abnormal. So it's hard for attackers to figure out the right balance there.
Is the confirmation dialog still iframeable and thus subject to the same clickjacking that it was trying to prevent?
No, it is not. We actually require it to pop out in a separate browser window.
We'll take that one last question like that.
Yeah, I'm just curious about what your process or workflows look like for apps that may have legitimate applications that may go rogue or get compromised. And so they're submitting both legitimate content as well as spammy content from
Yeah, so I'd say there are kind of two ways that we deal with that. One is sometimes what happens is the app will actually get enforced on, will get disabled, they'll submit an appeal and say, hey, what happened? And then we'll go talk to them and help them work through their security issues. And we've done that a number of times. And another way that we actually mitigate this is that there's actually a set of applications in the world that we know are good, like some of the examples that came up earlier in this. And we actually do whitelist certain select applications from our automated enforcement when we have a really good reason to believe that they're trustworthy.
Okay, we're out of time. I'm sorry. We can ask him after this. Sorry about that. Thank you so much, Jay Gross.
Thank you.
I want to share a quick story with Jonathan. So Jonathan is a firm believer that we can't change human behaviors. And I was like, no, I don't believe you. I'm going to try it anyway. So what we did is at the end of the education flow that Jonathan talked about, we launched an experience where we actually show people what their accounts have created when their accounts are compromised. And what ended up happening is we received a bunch of people saying, hey, where are my 5,000 free likes? Where is my pink Facebook? And people are really pissed. But I haven't lost hope yet. I'm still going to keep trying to educate people.